All right, so today we're going to talk specifically about weak acid and weak base equilibrium. We kind of touched upon this in the last lecture, but we'll go over it formally here. Right? So remember we talked about strong acids and how strong acids dissociate completely? Well, a weak acid, and my pencil's not working. Let's switch to this one. Okay, so a weak acid do not dissociate completely, right? How can you tell that something's a weak acid? It has a Ka value. If it has a Ka value, it's a weak acid. What's another way to tell if it's a weak acid? It's not on the list of strong acids. Okay. Now, generically, Hb is just a formula we use whenever we want to represent a weak acid. Okay. The B is not literally an element. It just represents some formula of an acid. And here's the generic reaction, right? The result of weak acid in water is that it will produce hydronium, H3O+. B- would be the conjugate base of the weak acid, right? In this case here, water acts as the base, and therefore hydronium would be the conjugate acid. If we needed to diagram this out, it would look like that. Right, so because there's an equilibrium, all weak acids exist in equilibrium. They're subject to the law of mass action, which means we can write an equilibrium expression. So hence, Ka, the A stands for, well, you guess, what do you think it stands for? Acid, right? So the equilibrium constant for an acid is the products over the reactants, just like it always is. Notice that we are excluding water, and that should be no surprise, because water is a condensed state. It has no measurable concentration. All right, so because this is an equilibrium problem, you work these problems exactly the same way that you work any other equilibrium problem that you've done in the past, right? So just jumping right in, if we have a Ka that is given to us for hydrofluoric acid, HF, and they want to know what's the H plus at equilibrium for a 0.25 molar solution. Now, the concentration that they give you in these problems is always the initial, right? They're always giving you the initial concentration, and the goal is always to figure out what the concentration of H plus is at equilibrium, right? Meaning here. So the setup, as expected, your initial concentration in the I row, right? Nothing here, nothing here. Plus x, because since we have zeros, it's very clear that we're going to be adding to the product side. Subtract x from here. And then after you apply that, 0.25 minus x. So, working out the math, Ka equal to H plus times F minus over the concentration of HF. And these values are given, or at least the Ka is given, so 7.2 times 10 to the minus 4 is equal to x squared over 0.25 less x. Right? Same simplification rules here apply. We're only 3 orders of magnitude apart here, so I wouldn't ignore the subtraction of x. I would just use it and leave it in there. So go ahead and use the solver. Make sure you get the same thing I get. .013. Okay. So the equilibrium concentration is 0.013 for H plus, but also for F minus, because it's a 1-to-1 ratio. And the concentration of HF at equilibrium would be 0.25 less x, which 0.237. Okay, if they want the H plus at equilibrium, usually they want the pH as well. So just go ahead and take the negative log of what you have for x. And our pH for this is going to be about 1.88. Okay, This is your basic, no, not basic. This is your standard weak acid problem, right? Very, very typical. Can you find the pH? Can you find H plus if you're given the Ka and the initial concentration? Okay. So let's talk about bases, weak bases. Many substances that do not have OH minus in their formula behave as bases. Now, the obvious bases are the strong bases, right? You look at NaOH, you look at KOH, and you say, oh yeah, clearly that's a base, right? There are bases that are not obviously bases. So generically, when we want to represent something as a base in a formula, this is your base, your general formula. We use B minus, right? B minus, because B minus is the conjugate of HB, right? So your KB expression is set up the same way as your all equilibria, products over reactants, excluding the condensed states, and now this is KB. So to solve for the pH of a weak base, mechanically, this is the same thing that you've done before. Ice table, initial concentration, plus X minus X, and you will need an initial concentration, and you will need the KB. So 5.6 times 10 to the minus 4 is equal to X squared over 0.15 less X. But the thing that you must remember is that because this is a base, X is going to be equal to OH minus, not H plus. All right, so you just got to remember that, because when you calculate pH, you have one extra step. All right, so grinding this out, we get 0.0089, right? So if I said, what is the, so we have the OH minus concentration, and they also want the pH. Taking the negative log of this will not give me the pH, right? The negative log of this will give me the pOH, right? Because it's an OH value that I have. So I need to subtract 14 after I do the negative log. All right, so pOH is 2.051, so the pH will be 14 less that, 11.95. Okay, it's definitely basic. So common weak acid, common weak bases, this is how you go about it, solving for the equilibrium concentrations and the pH. Notice how the equilibrium setups are a lot less complicated than some of the equilibrium problems that you have seen in the last unit, right? These equations, these balanced reactions, they rarely have coefficients, which means almost you're not seeing anything cubed or quadruple, raised to the fourth power. You're not seeing any of that, right? You're not seeing plus 2x or minus 2x. It's a lot more straightforward, right? Because the reactions are pretty simple. Okay. So the next thing is to talk about salts. First, let's identify what a salt is. A salt is an ionic compound that contains cations other than H plus and anions other than hydroxide and oxide. All right, or maybe another way to state this is it's an ionic compound that does not contain H plus, OH minus, or O2 minus. That's how we define it sophomore year, and maybe that's an easier way to think of it. It's an ionic compound that's not an acid or base. All right, in short. It's not literally just NaCl. NaCl is an example of a salt, but it's not the only salt. All right? So, The thing is, when you have an ionic compound that is soluble, it dissolves into ions. And these ions may react with water, they might not. So we need to learn a little bit about ions. So first, there are some ions that are neutral in water, meaning they don't react with water. The first batch is Cl minus, Br minus, I minus, NO3 minus, ClO4 minus. I would even add ClO3 minus. Those should seem familiar somehow. What do they have in common? Where do you recognize them from? Read?
They're strong acids.
Yeah, they are the conjugates of strong acids. Right? HCl, HBr, HI, HNO3, HClO4, HClO3. Notice that there's one missing. What conjugate is not there from a strong acid?
SO4.
Right, from sulfuric acid. That's a special case. We're going to talk about that one later. Right? So the rule is conjugates of strong acids are inert. They do not react with water. If they do not react with water, that means the water will remain neutral. Okay. Let's look at some cations. Lithium, sodium, potassium, calcium. That should be barium. There's an A missing there. Barium, strontium. Where are those from? Strong bases, right? Conjugates of strong bases are inert also. Okay, so this is another reason why it's important to memorize the strong acids and strong bases. Not because there's going to be a test question where I ask you what are the strong acids and strong bases, but you need to know when these ions appear that if there is some acidic or basic behavior, it is not because of these. It is because of something else. Okay? This will become more apparent through more examples. Many anions are basic in solution. Here's just a sampling of some anions. Okay? Now, let me demonstrate. If I picked any one of these ions, like, so for example, CO3 2-, this is carbonate. So if I have carbonate, actually, let me back up. Let me write the salt first. Let's say I have a compound, sodium carbonate, right? And let's say I dissolve it. So I get 2 sodium ions and I get the carbonate ion, okay? All right, this is a simple dissolving equation, no big deal. I've just dissolved carbonate. But the thing is, if I took a pH strip and dipped it in the solution, it would not be neutral. Right? The pH for this is roughly 12, which seems kind of weird. Why in the world? 12 is really basic. Why would this be basic? Well, what are the products? There are 2 ions. And of these 2 ions, didn't we have a list of ones that would not react? Is one of these ions on that list? Which one? Yeah, sodium. Sodium is inert, okay? So sodium is inert. Therefore, whatever is happening is being caused by carbonate. So the reaction is this. What you do is you write what's called a hydrolysis equation, and that means reacting the ion with water and resulting in either an acid or a base. So if the pH is 12, that means hydroxide was made, right? If hydroxide was made, that means the water must have acted as the acid, the carbonate must have acted as a base, and the result is this. That is how we explain the pH of 12 when I dissolve sodium carbonate in solution. Right, and you can link these up. So the conjugate acid is that, the conjugate base is this, so they're linked that way. Okay. If there are negative ions attract the proton from water, and then they behave as bases. The result is OH minus. Now, Do all negative ions behave as bases? No, because look, you have a list right here of exceptions. Okay? Also, there are some exceptions right here. These guys, I'll write it larger, HSO4, which is known as bisulfate, and H2PO4 minus, these are anions. They both have negative charges, right? This is dihydrogen phosphate. It's a polyatomic ion. Both of these are on your polyatomic ion sheet. These have negative charges, but they are not bases. They are actually acidic. And so how do you prove that they are acidic? Well, you write a hydrolysis equation. H2PO4 minus plus water becomes HPO4 with a -2 charge, and hydronium is made. Acidic. All right, there's no other way around it than to just memorize these two. Okay, you just got to know them, okay? They're going to pop up. You don't want them to throw you. Okay, so if negative ions are basic, well, what about cations? So not all cations are acidic, but a bunch of the common ones are. And they are, well, here. 4 common ones plus ammonium. So really 5 common ones that you need to know. Copper, zinc, aluminum, iron. And the way that you remember them is just to remember cousin Alfie. Cousin Alfie is an acid. Okay? What do we mean that they're an acid? Well, so the copper and zinc ions both have a charge of +2. Okay? Aluminum and iron both have a charge of +3. So what happens is, let's say I had something like copper nitrate. Copper nitrate ionizes to form the copper ion plus nitrate ions, right? But if I tested the pH of this, the pH would come in around in like the high 3s, okay? pH roughly 3.8 or something like that. Why would this be? Well, here's what happens. When we studied complex ions, we know that transition metal ions that are highly charged and compact, like small, can attract and form ions with ligands. In this case, the ligand is water. All right, so 4 water molecules. Why 4? Just it happened, the magnitude of charge dictates the number of ligands, and in this case, it's generally twice the charge. So the result is we get an ion that looks like this. Okay, so yeah, that should make sense, right? But here's the thing. That ion right there, that picture doesn't explain why this is acidic. So what happens is this. Once that complex is formed, one of the water molecules has a proton dissociated. And therefore, we no longer have 4 intact water molecules. We only have 3 intact water molecules and the remains of the 4th. So if I were to draw a picture to help illustrate that. Okay, so here's copper, right? Here's one water. Here's another water. Oops. Here's another water. Here's the 4th water. Right? This right here, that's this guy. Does that drawing make sense? Okay. But one of the hydrogens comes off. And if it produces an H plus in solution, by definition, it is an acid, and the concentration of H plus will go up and the pH will go down. So what does this look like after it comes off? They're separated. And notice the charge goes down because your charge started as +2, but by losing an H plus, the charge, your charge has to be conserved as part of the balancing process, right? So if there's an H plus produced, that means the residing charge on that complex ion is now +1 instead of +2. Okay, these 4 ions do this. They undergo the same process, okay? Copper and zinc react identically. If I said write this hydrolysis reaction for zinc, then you would just replace Zn in place of copper and everything else would be identical. Now, we can combine and shorten these, right? So really, it's these two equations that really show what happens. And we have an intermediate, which you can just cross off. So you can actually just write the equation as this goes to this, right? Algebraically, when you combine them, you're just canceling the intermediate. All right, what if it's aluminum and iron? Well, notice the charge on aluminum and iron is +3 and +6, and therefore the coordination number is different. It's now 6 instead of 4. The same process happens. The only difference is you start with a different number of waters at the beginning, and your charge is different. But the process is the same, and the writing of the equation looks very, very similar, but instead of reacting with 4 waters, you react with 6 waters. Okay, so like this, okay? Well, actually, just like this, right? So I have already canceled the intermediate. Can someone tell me what the intermediate's right here, right? So this is what we end up with, but just to rewrite it in the same format as the other one, it would look like this. Stop, take a look at that, see if that makes sense to you. One of the waters breaks, releasing an H plus, and that is why it is acidic. Okay. And I said that NH4 was acidic. Right, this guy, NH4. Well, look at it. It's got an H plus on it, right? NH4 plus produces NH3, and the H plus pops off. Now, something to mention about hydrolysis equations. If I wrote this equation shown reacting with water, the net result is exactly the same. The only difference is we write H3O plus instead of H plus. Okay, these two are the same, so it doesn't matter which way you write it. If you want to include water as a reactant, that means you'll have H3O plus as a product. But if you leave water out, you end up with H plus as a product. And remember that both H plus and H3O plus are the same concentration, so that's why effectively these two equations are the same. So it doesn't matter which one you write. Okay, for acids at least. For bases, you do need to show the water. So base hydrolysis, if I were to pick another one like CN minus, cyanide, the reason why you have to show water is because you have to show where the hydroxide comes from. And if you don't have water on the left side, then OH minus would have come out of thin air, and you can't have that happen, right? So water needs to be included with bases. right? Otherwise, you'll be violating the law of conservation of matter. Okay, so there are a bunch of formulas here. Let's go around and let's reason out why some of these are either acidic or basic or neutral. Okay, so the first formula, sodium fluoride. Sodium fluoride is this. The first thing you do when you write the formula is you need to go through your mental list of the ions that are conjugates of strong acids and strong bases. Do we have, are either one of these two ions part of a strong acid or a strong base? Which ones? Na. Na is from sodium hydroxide, right? So that means Na is removed from consideration. So really what we have then is F minus. Is F minus from one of those strong acids or strong bases? It is not. It is negatively charged, therefore how's it going to behave? Yes. This is a basic salt. Okay. Zinc nitrate. Right, so you have zinc, you have Zn2 plus, and you have NO3 minus. You have to rule out your ions first before you make an assessment. Which one of these, if any, can we rule out? Nitrate. We were unable to rule out zinc. Should you know something about zinc? Maybe a long lost relative who lives in Arkansas who barely has any teeth? This is your cousin Alfie, right? Zinc is part of his cousin Alfie. So this is acidic. Don't ask me where that reference came from. It just sounded like someone who lived in Arkansas. Iron 3 chloride. No offense to people who live in Arkansas. A few people are watching this from YouTube. Iron 3 chloride. What can you rule out? Chloride. This. So what will this be? Acidic or basic or neutral? Acidic. All right. I want you to take a few minutes and do the same to the rest of these, and then we will discuss. All right, if you didn't finish, that's okay. We're just going to start talking about them. Okay, so lithium iodide. The ions present are Li plus and I minus. What can you rule out? Both. Oh, interesting. So I have two ions, both of which are known to be inert. The result, if I dissolve this solution, make a solution of this, the pH will be what? Yeah, neutral, right? Okay, if both ions are inert, then nothing happens. Then there's no acid or base interactions. There's no OH minus made, there's no H plus made. Okay, ammonium nitrate. NH4 plus, NO3 minus. Will this be acidic or basic? Or neutral? This will be acidic. Because NH4 plus ammonium is a weak acid. Sodium acetate. Let's change colors up here. Sodium acetate, Na plus, C2H3O2 minus. Will this be acidic or basic? What do you think? Yeah, it's going to be basic. We can rule out sodium. And that's a negative ion, so therefore this is basic. Okay. Potassium cyanide, K plus, Cn minus. Acidic or basic? Basic, yeah. Potassium is ruled out. We have a negative ion. This is basic. Trimethylamine. Ooh, this is not a polyatomic ion, but you should know something from our organic unit about some words in here. Amine. What does amine mean? Does it mean it's not nice? It's a bad person? Trimethylamine. He's 3 times as mean? What does that mean?
NH2.
Yeah, it's basic. Amines are basic, or bases. Right, so it would actually look like this. Amine, so trimethyl, so CH3, 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 and then lone pair. Aluminum bromide. You got Al plus 3, and you got Br minus. What is this, acidic or basic? This is acidic. Oh, look, it's conveniently placed right above the equation that shows how it's acidic. Right, it's acidic. Strontium, Sr2 positive, nitrate, NO3 minus. Acidic or basic? Neutral. Neutral. Potassium hydrogen phosphate. Okay, so there are polyatomic ions with long names. So potassium is K plus. Actually, you'll have 2 of them because hydrogen phosphate is HPO4 with a -2 charge. What do you think? This will be basic because the potassium is inert. And then sodium dihydrogen phosphate. So here's sodium. Dihydrogen phosphate is H2PO4 with a -1 charge. Acidic or basic? I had you asterisk this earlier. Dihydrogen phosphate. Something's weird about this because at first glance it's got a negative charge, and you see a negative charge, you think, oh, basic, but this will actually be acidic. All right, it's a special case. How are we doing, guys? Can I give you a salt? And can you pick it apart and rule out what ions you need to make predictions about it being either acidic or basic? And then write an equation which verifies that. Okay, so let me just give you 2 more. Let me just find some room here. Okay, so how about this guy? So what do we say, acidic or basic or neutral? Eva, what do you think about this guy? Acidic. Can you explain to me how would I write an equation to show this guy's acidic? Okay, I'm gonna stop you there. So definitely reacts with water, but this is your relative from Arkansas, right? And they always band together, like in groups. And since zinc has a charge of 2, how many waters should we associate with it? Yeah. So then we get like a conglomerate. And, it's going to take you guys a little bit of time to memorize those ions, right? But we did test this pH, and we saw this pH was about 3.5. So we know there's H plus made. What is my next step to show that H plus is made? The second half of this reaction will look like... Yeah, let's break it. Let's break one of the waters. So instead of H2O4, now what's the rest of this formula? 3OH, yes. Is my charge still +2? It's +1. And what's my other product? H plus, yes. Okay. That is as far as we should go today.